Hi everybody, welcome back. In this video we're going to go over the first part of section 14.5 and talk about directional derivatives and gradients. First, let's just review what partial derivatives do. Remember, the partial derivative tells us how a function is changing in either an x or a y direction or a z direction if you have a third variable, but for now let's focus on functions of two variables. So remember, if I take a partial derivative with respect to x, that's telling me the rate that f is changing in the x direction, or in the I direction. If I take a partial derivative with respect to y, this is the rate that f is changing in the y direction, or the j direction, right? This j vector. So that a natural question would be, can we look at the rate that f is changing in another direction, right? This seems pretty restrictive. I can only look in two directions, or their opposites. And the answer is yes, we can look in another direction, any direction we want, at a fixed point. That's called a directional derivative. And if we look at the definition of a directional derivative, it's given in terms of a limit, as are most things in calculus. So the directional derivative, and we're just going to deal with a function of two variables for right now. So the directional derivative of a function f at a fixed point x naught y naught in the direction of a unit vector, ab, so this has to have magnitude 1, is defined as, this is notation, so a capital D with a subscript vector u, f of x naught y naught, that's the directional derivative of f at the point x naught y naught in the direction of u, is defined as the limit of f of x naught plus ha, y naught plus hb, minus f of x naught y naught over h as h goes to 0, if that limit exists. So now, if we take a look at what's going on here, if we ignore this limit for a minute and just think of what we can, this term, as h increases or decreases, we're starting at the point x naught y naught, and then going in the AB direction, the u direction, in the amount of h. So we're at a fixed point, and then we're traveling in that direction. It's a line segment, right? And it stops whenever we stop h. So we're just traveling along a line. But the point is that what we're doing is starting at a point, traveling in a direction, and that's how we get the directional derivative. Now, just like other derivatives in calculus, we're not going to use this limit definition to actually compute directional derivatives. So how are we going to compute them? So I'm going to go through a derivation just to give you an idea of how this works. You're not going to be responsible for remembering this or memorizing it, but just to give you an idea, how can we somehow compute these things? So first, I'm going to define this function g. That's just a function of one variable, this h parameter. And so if you actually look at what I'm defining g as, it's f of x naught plus ha, y naught plus hb. It makes sense to define it in terms of just h, because x naught, y naught, that's a fixed point. ab, that's a fixed vector. The only thing that's changing here is h. So I can define it as a function of one variable. And if it's a function of one variable, I can think about its derivative. Its ordinary derivative, so g prime. And let's look at g prime of 0. If I use the definition of a derivative that you learn in Calc 1, g prime of 0 is equal to the limit as h approaches 0 of gh minus g0 over h. But if I go back and use this definition, what is gh? What is g0? G of 0. G of h is exactly this term. And g of 0, if I plug in 0 for h, I get exactly f of x naught y naught that I forgot to put here the first time I wrote this. And this is exactly the definition of a directional derivative. So far, we can represent this directional derivative as a new function, its derivative evaluated at 0. So that doesn't help us actually compute this thing yet. But let's take a second perspective and say, okay, instead of defining this as a function of one variable, what if I define each of these components as functions of one variable? And say, okay, now I'm going to define this x of h function. That's just going to be the first input here. It's still just a function of h. This y of h function is going to be the second variable here. Still just a function of h. Y naught and b are fixed. Now I have that g of h, this function of one variable, is equal to f, a function of two variables, where each of these variables are themselves a function of h. So now if I think about the derivative, I can use the chain rule that we learned in the last lesson. So the chain rule says, if I want to find g prime of h, or dg dh, that's equal to the partial derivative of f with respect to h times x prime, which is dx dh, plus the partial derivative of f with respect to y times y prime, which is dy dh. But I can go back and look at how I've defined x and y and actually take these derivatives. If I take the derivative of x with respect to h, that's just a. I take the derivative of y with respect to h, that's just b. And I can plug those in. So g prime of h is equal to partial derivative of f with respect to x times a, plus the partial derivative of f with respect to y times b. Now, I can take these two perspectives and say, okay, this directional derivative is equal to this quantity evaluated when h is 0. Well, what happens when h is 0? I just get the point x naught, y naught. So let me explain this notation here. I'm saying that g prime 0 is equal to the partial derivative of f with respect to x, this big line here, and the point means evaluated at this point x naught, y naught. So we take a partial derivative, and then we plug this point in, times a, plus the partial derivative of f with respect to y evaluated at x naught, y naught, times b. Written in a different notation, perhaps a simpler notation. This is still a partial derivative using subscript notation, evaluated at x naught, y naught, times a, plus this partial derivative with respect to y at x naught, y naught, times b. And this gives us a formula to actually evaluate a directional derivative. So the directional derivative of f in the direction of u at the point x naught, y naught is given by this quantity. And this formula and this result is summarized in the theorem here. So if you have a differentiable function of x and y, which means the partial derivatives exist and are continuous on the domain, then it has a directional derivative in any direction, as long as that direction is a unit vector, and it can be computed using that formula. So this was for differentiable functions of 2 variables. If we look at differentiable functions of 3 variables, then we see that it is quite similar. The only thing that changes, hold on a second, sorry. The only thing that changes is now our unit vector has a third component. Our function is a function of 3 variables. And our definition of directional derivative has a third term that we're adding together. It's the partial derivative with respect to z times the third component of that unit vector. So now if you look at these two formulas for functions of 2 variables, functions of 3 variables, you might say, hey, that kind of looks like a dot product. And it is. We can represent this as a dot product. And the dot product that we get, here it is in 2 or 3 variables, the directional derivative of f in the direction u. In 2 variables, it can be written as a dot product between this vector of partial derivatives and the direction vector. Same thing in 3 variables, where now we just have a third partial derivative, and our unit vector has a third component. These both have to be unit vectors. So we know how to characterize these. These are unit vectors. We call them u. Is there some way that we can characterize this vector, or some notation we can give this vector? It turns out it's actually a very important vector that we're going to be using pretty much the rest of the semester. It's called the gradient vector. So if f is a multivariable function, then we define the gradient vector. This is the notation. So it's this triangle. Some might think of it as an upside down triangle, but it's just a triangle. It's the del operator, or some people call it the nabla operator. So the gradient of f, it's the vector of partial derivatives. So in 2D, it's the partial derivative of f with respect to x is the first component, partial derivative of f with respect to y is the second component. In 3 dimensions, if we have a function of 3 variables, the first 2 components are the same, and then we add a third component, it's the partial derivative with respect to z. If we had a function of 4 variables, the fourth component would be the partial derivative with respect to whatever that fourth variable is, etc. You can have as many variables as you want, make this gradient vector as long as you like. Now that we have a gradient vector, we can represent the directional derivative as just a simple dot product. The gradient of your function f dotted with the direction vector u. And that's how we're going to compute our directional derivatives. Now, we still need u to be a unit vector, and you might be wondering why I'm insisting on u being a unit vector. Well, there's another perspective that you can take of directional derivatives, which says that we can think of them as scalar projections. And in particular, you can think of it as a scalar projection of the gradient in the direction of u, where you want to take your derivative. So if you remember the formula for a scalar projection, we're going to project the gradient onto the direction u. It's the dot product of the two vectors, so the gradient dotted with u, divided by the magnitude of u. Well, I keep insisting that u needs to be a unit vector because in that case, the magnitude of u is just 1, and we get our definition of a directional derivative. And so now you have another way of thinking of directional derivatives. It's just a projection of the gradient in a certain direction. So you compute the gradient, you pick the direction that you want to go, and you look at how much of the gradient is going in that direction. And that's your directional derivative. If you look at the partial derivatives, we already know the partial derivative with respect to x is going in the x direction, the 1, 0 direction. So if I project the gradient into that direction, I would get precisely the partial derivative with respect to x. Likewise, if I look at just the y direction and I project the gradient into the y direction, the scalar projection, I get the partial derivative with respect to y. If I have a function of 3 variables, I project in the z direction, I would get the partial derivative with respect to z. So this corresponds with the partial derivatives we already know. And now we're just projecting this vector in different directions, the scalar projection, because the directional derivative is a scalar. Now to finish up, we're going to take a look at a couple of examples, and in the next video we'll talk about what the geometric interpretation of the directional derivative is. But for now, let's look at a couple of quick examples. So first, find the directional derivative of this function f, 4 minus x squared minus 1/4 y squared, at the point 1, 2, in the direction that makes an angle of pi over 3 with the positive x-axis. Assume that this direction vector has all positive components. So what does this mean? We're not given a u here. We don't know what u is yet. We know what f is. We know the point we want to evaluate the directional derivative. Well, what we're doing, if we look at this x and y axis, I want to go in this direction. This direction that makes an angle of pi over 3 with the positive x-axis. And the reason it says assume all positive vector components is because we want to go in the first quadrant. We don't want to go in the fourth quadrant or anything like that. So this is the direction we want. The way we can figure out what vector represents this direction is using this very important unit vector. Now, this unit vector, cosine theta, sine theta, it is a unit vector. If you take the magnitude, it's going to be the square root of cosine squared plus sine squared. And cosine squared plus sine squared is 1, so it's the square root of 1, which is 1. And this unit vector, cosine theta, sine theta, given an angle in the xy plane, gives you a unit vector going in the direction that that angle makes with the x-axis. So if I plug in pi over 3, which is what I want to do, that'll give me my unit vector going in the direction that I want. So here I have my unit vector u is 1/2 square root of 3 over 2. I need to compute my gradient, so I need to go back and look at this function, take the partial derivative with respect to x, and I get negative 2x. Partial derivative with respect to y, I get negative 1/2 y, so there's my gradient vector. So I have my gradient, I have my unit vector, my direction. I could just dot these two, and then plug in the point 1, 2. You can also plug in the point 1, 2 for x and y, and then dot them. Either way, it doesn't matter. I'm going to go ahead and plug in 1, 2 first, and then dot these and see what we get. So if I plug 1, 2 into my gradient, that gives me negative 2, negative 1. And then I dot these. Remember that when you dot, you get a scalar. So I perform the dot product and I get negative 1 minus root 3 over 2. And this is the directional derivative. This is the answer. It's the directional derivative of this function f in this direction here. So in the next video, we'll take a look at the geometric interpretation of our directional derivative. And I'll do another example, and we'll talk about more properties of the gradient and properties of directional derivatives. All right. I will see you all, well, whenever you click on the next video. I don't know when that'll be. Hopefully soon.